So in addition to knowing what physical evidence is and the importance of it and knowing about individual and comparative analysis, we also need to talk about things called individual and class properties. And first we're going to sort of talk a little bit about the probability. So again, remember, part of this probability is we're trying to say the probability that there is a very, very high probability that that this item has this identity, or that this item and this item came from the same source. So probability, of course, is the frequency that an event occurs. And in some cases it's very easy to determine, like flipping a coin. There's only two options. They're equally possible, so it's a 50% probability that you'll get a tail on a single coin flip. But in a lot of other things, probability is really hard to assess. Sometimes we can't measure it directly. Sometimes we can take a sample and get an idea of what the probability is. Also, we're going to talk about the product rule of probabilities. If I want to know if I know individual probabilities of several different distinct occurrences, and I want to know what is the overall probability that all of those things occurred, I can multiply the probabilities to get the overall probability, and we will use that, and that's very powerful in dealing with some class evidence. Okay, so I want to just kind of back up and talk about natural and evidential limits. So there are limits on the properties that I can, inevitably I'm going to analyze it and I'm going to measure some kind of property. That's what I want to do in my analysis. And we have different techniques to try to measure things, but it's important to understand that natural variations in objects can become, as I can get better and better at measuring something, I recognize that no matter how good I get at recognizing something on a particular item, that property has a little bit of variability to it. And I'll give you another example in a minute. So there's natural variations, and so sometimes if I keep measuring with high sensitivity, I'm going to get different answers, not because I'm actually testing different kinds of evidence, but because that evidence alone has different variations to it. So what that means is that if I can continue going, if I take two pieces, there are no two pieces that would ever be considered identical. Everything has some kind of variation to it. And then there's also variations in the evidence. So like if I take a hair sample, truthfully, I might have to take 25 hair samples because there's a variation from person to person in evidence. And so having these variations can be kind of complex, and that's going to mean that all of this evidence analysis, it's somewhat of an art form, as opposed to just like, oh, there's a magic answer and yes, it's a match, or no, it's not a match. It's not quite that simple. So this is just kind of showing you the concept of what we mean about variation. Okay, let's say that these are measurements of different metals and a property called density. So I can measure the density of different metals. And you'll notice for the most part that as the metal changes, so does the density. So aluminum has a specific density, zinc has a specific density, and notice there's a little bit of width to these. And that width is saying, well, if I took many, many samples of tin, they're all the same thing, but it can vary. So I might get a slightly different density depending on the specific sample that I have. So it has some natural variation. Also, if I kind of look a little close up at a couple of these, there was a couple of them that are close together. Look over here. The variation of these is really almost overlapping. So it would be really difficult to distinguish nickel and cobalt. They have almost the same density with similar variation, so that even copper's, if I took a measurement of a copper sample and it was on the lower end of its range of densities, and one of cobalt that was on the higher end, they're hard to tell them apart. And this complicates things. Similarly, if I were to kind of do these measurements, the measurement itself has some kind of error to it. So my measurement itself has sort of a range of possibilities. I make a measurement, I get a number, but it can have some error to it. And so I have to consider the boundaries of that error as well. So for instance, let's look at some examples of how this can complicate things. So let's say I measured sample 1 and its density was 3. The measurement of this sample 1 had a density of 3 and the error in that was 0.3. So my measurement technique meant that it's somewhere between 2.7, that's 3 minus 0.3, and 3.3. So I have a range of possibility values that I've measured off of this. Sample 2 has a density of 8.85, but its measurement precision is 0.05. So that means somewhere between 8.80 and 8.90. I've subtracted 0.05 and added 0.05. And so that's as good as my technique could get for that particular one. Now, if we look at that on our range of metals, note that sample 1 is here, so it's really wide. It was a 0.3 error measurement. But when I go up to matching it, there's really only one close by with natural variation, and that would be aluminum. So I could still say sample 1 is aluminum. They're kind of overlapping, not by much. And even though it wasn't a precise method of measuring it, I have a pretty good idea that the identity is aluminum because all the other metals don't have densities anywhere near that. Whereas if I took sample 2, remember sample 2 had a much more, instead of 0.3 error, it was 0.05, much smaller error or a higher precision, and yet the particular value I measured was in an area where that really matters, right? So I really wouldn't be able to say which one of these is because this kind of spans all 3 of these options. So I really wouldn't be able to say whether it's copper or nickel or cobalt. So even though it's a better method, based on the specifics of what I'm trying to measure and the natural variation and the differences between different similar metals, it would be more confusing. So it'd actually be more, I would be more probable that sample 1 is aluminum than I could say that sample 2 is copper, for instance. So this is where conclusions and the specific evidence in this measurement gets really tricky. I'm not expecting you to be able to do this kind of analysis. I'm trying to show how this natural variation in probability really makes the conclusion part of an analyst's job pretty tricky at times. Okay, so now I want to talk about different kinds of properties we can measure. We can classify characteristics. When I say characteristic, it might be density, it might be blood type, it might be loci of DNA. So it's a specific thing that I'm going to measure. So I'm looking for if the property can be associated to a single source with an extremely high degree of probability, we call that an individual characteristic. So in the case of density and aluminum, that's like an individual characteristic, right? That density is associated with a single source with a very high degree of probability because in that particular case, there's none that are anywhere densities nearby. That would be an individual characteristic. And I'll give you some examples of some other individual characteristics. So if I have evidence for which I can measure that kind of a characteristic, I'll call that individual evidence. So individual evidence parallels off with something that I can measure an individual characteristic of. Class characteristics is a property that can only be associated with a group. I can't say it's a specific single source, but I can narrow it down to a group of sources. And then that would be a class characteristic. So evidence for which I can measure a class characteristic is called class evidence. And let's give you some examples of these individual and class characteristics. Just reminding you that even with individual characteristics, it's never possible to say with exactness that this sample I measured is exactly this came from this source. There's always a little bit of it because of those variations in evidence and natural variations. I can never really say for sure, but I can say with a very high degree probability in many cases. So we say that the probability is so high as to defy mathematical calculations or human comprehension. So, you know, that the likelihood is 999,999 out of a million. So it's like 1 in a million chance that we could be wrong in this assignment. And so I need very high probabilities to be considered an individual characteristic. Some examples are 2 fingerprints. So ridge characteristics of 2 different fingerprints. The likelihood that two things would have those same matching ridge characteristics if was analyzed by a good analyst is very small. So I can pretty much say with strong certainty that these two fingerprints had to have been made by the same person. Random striation markings on bullets or on tool marks, so and we'll talk about this in the chapter, is that it's not so much the bullet itself, but when it's fired, there's markings left off of it by variations inside the gun that are unique and individual, so that now I can say this bullet was shot from this gun. It came from a single source, so I can compare a bullet that was shot from that gun to a bullet at a crime scene, and if they have those same striations, I say this bullet came from that same gun. Irregular and random wear patterns in tire or footwear impressions. Again, it's not so much the tread, right? I might find multiple sneakers with the same tread pattern, but the wear pattern on them and the individual markings is what's going to make it unique to this particular shoe. So that would be an individual characteristic. Handwriting characteristics. Objects that can fit together like a jigsaw puzzle. Sometimes these plastic bags that were made in sequence, or things where you have them on an assembly line, and this plastic bag and like a garbage bag where you perforate them. In the process of making them, because they were made together, the striation marks running across the bag, sometimes I can say that, okay, this plastic bag at the crime scene was in the same box with this one at this person's house, so this bag came from that box and therefore had to be from that person's home. So that's a individual characteristic. Now, class characteristics are going to be a little bit more general. So I might say that this nylon fiber has a particular chemical composition or dye pattern that matches this manufacturer's. But when a manufacturer makes a sweater, for instance, they're going to make many sweaters, and all of those sweaters would have those same chemical composition and color patterns of the nylon fibers. A type of ammunition, right? If it's an unspent bullet, or if I don't have a suspected weapon, I can say that this is a 38 bullet, but I can't say that it was specifically shot from one particular gun. A tread pattern or of a shoe print or a tire print, so maybe I can't get the individual wear pattern markings, but I can say this is a size 8 Air Jordan, but there would be many size 8 Air Jordans. Color, diameter, medullary index, and shape of a hair. Again, you don't have to know what those specific properties are, but the idea is that I can look at hairs and say, okay, I can match them to a range of possible hairs, but I can't match it to, this came from this person's head. Chemical composition or refractive index of plastic or glass. So maybe I can't match up the actual pieces of the tail light and say they came from the same taillight, but I can say this plastic from this hit and run crime scene and this plastic from this suspect's car taillight have these same properties of the plastic, and the likelihood is that they could have come from the same car. It doesn't say that it had to have been, because there might be other cars made by the same manufacturer that have very similar plastic as well. Blood typing, being able to say what type of blood it is. Hair color would be an example, right? Blonde headed, right? There's a class of individuals that does rule it down, because that means it rules out people with brunette hair and red hair, but it doesn't tell you necessarily that it was this particular person with blonde hair. So again, we kind of point out this need for statistics. So one of the things that's really important with class evidence is that because it's still a variety of possible, it only narrows it down to being in a group of people or a group of objects. I want to now be able to look at the probability. So what is the probability that a nylon fiber originated from a particular sweater, or that a paint chip came from a suspect car in a hit and run? That means I need to know what is the natural probability of those sweaters. Like, what is the likelihood that a sweater would be that sweater? So I need to know some probability about it. Or the paint chip, what is the likelihood that this paint chip could be, how many cars are out there with this same color paint, and can I narrow it down to the likelihood? And unfortunately, for a lot of our characteristics, we don't have that evidence. We don't have those probabilities. If I have them, I can say that, so if you can show that the criminal, the suspect, was redheaded, there's a very low probability of red hair compared to blonde hair. And so that can sometimes help me narrow it down and say, well, even though that I still don't know that it was this particular redheadedness is so rare, it's only 1% of the population, so I've narrowed it down to it's a very small group. So again, there's not much statistical data available for all of this, and one of the big goals right now of forensic scientists is to gather this statistical data. So if part of the job is gathering statistical data, how many redheads are there in the population? How many blondes are there in the population? What is the probability that somebody has blood type A versus blood type O? And creating them and creating statistical databases with them that can be used for analyzing the likelihood of class evidence. So this is a huge push on a national level in the United States, probably internationally as well. Since about 2014, there have been some analysis showing how poorly our statistical evidence is, and really pushing for better quality statistics, which means gathering a lot of evidence and making databases. So just kind of being clear that sometimes evidence isn't clearly class evidence or clearly individual evidence. There are limits, and there's sort of definitely discussion. For instance, we talk about DNA as being an individual characteristic that I can measure DNA loci and determine with almost near precision that I've matched it. But how many matches do I need to have to say I have a certain match? In paint chips, a lot of times there's layers of paint in automotive paint, and how many colors do I need to test and have to match to say this is a match? How many ridge characteristics are enough to individualize a fingerprint and say, now this is definitely an individual match? If you just have 3 characteristics in common, is that enough? Do you need 4? So all of these have limits. Like, when is enough? We talked this a little bit about when we talked about measuring an identification characteristic, is that I have to determine like how many tests and the number of them that need to exclude all the other possibilities. And so these are definitely not clear-cut answers, and this is an active area in law. In other words, remember, the value of evidence is determined by a jury, and a good prosecutor or a good defense attorney can really get into the gray area in these characteristics. As you might think that you have fantastic evidence with really high probability of assignment, and a good defense attorney might be able to call it into question and get the jury to think, well, I don't really know how good that evidence really is, or vice versa. Sometimes weak evidence by a good prosecutor can be considered like, well, even though this seems weak, when I take all of this together, all of these probabilities together make this so improbable that I could have misassigned it to anyone else and get a successful conviction. So again, the class evidence is, and the strength of class physical evidence means we need to be able to provide corroboration of the events with the data that are as nearly as possible free from human error and bias. So what that means is that I'm trying to make a case that the likelihood that all of these class characteristics in this one piece of evidence could have come from anything other than what I'm saying they came from. So either the piece of physical evidence or the suspect, properties of the suspect, that this has to be it. That's our job as forensic analysts. So if I'm dealing with more than one type of class evidence, the collective presence can, this goes alongside with, even though we're talking about physical evidence. Physical evidence doesn't exist in a vacuum. It goes along with all of the other investigative techniques that occur. And so interviews, right? So it's not just the value of the physical evidence, but does the physical evidence match up with the interview? And when it does, we're saying, hey, well, what would be that likelihood that these are all so consistent? All of the details are matching up. The location, the alibi or the not alibi. And so that's where we really get this extremely high degree of certainty. We might talk about, a variety of circumstantial evidence actually becomes proof. So again, and just reminding you that at the end of the day, there isn't a scientific analysis on how valuable or how likely or unlikely something is. That's going to be decided by a jury. So I do want to bring up that as you have different objects linking an individual to a crime scene, so does it's like I have a variety of different objects, right? It's not just the DNA or just the fingerprint, but I have now several different items. And I can exclude or exonerate by one piece of evidence. And that, this is the importance of getting these standard or reference samples, is being able to clear people. And that's a good thing. If I can clear suspects and exonerate them, I now can focus in on the appropriate subjects for suspects. So I do want to talk about the product rule of statistics. Again, this is now when I have multiple different pieces of evidence and each has its own probability. I can multiply those probabilities together. I have to do it with the probabilities in a decimal form, not in a percent form, and I can get the overall probability. So we're going to multiply the probabilities of each of the individual things we have. Let me show you an example. Okay, so if I talk about I got a blood sample and I analyze it and I find, you don't need to know what these factors are, just know that this blood had factor A found in 26% of the population, and it also had ESD, particular enzyme, found in 85% of the population, so fairly high probability for that one. And PGM 2+, 2- found in 2% of the population, so a fairly rare type of blood factor. So what is the probability that such an overall blood sample exists in the population? So I want to know, how rare is this particular blood, all three of these together. So I'm going to multiply the probability of having A times the probability of a person having ESD times the probability of a person having PGM 2+, 2-. We don't even have to know what we are, we just have to be able to find those probabilities and know what to do with them. So notice that I'm converting each of them into decimal by dividing by 100. So 26 divided by 100 is 0.26 times 0.85 times 0.02. And I get an answer of 0.00442 on my calculator. Now, to determine what is the likelihood that this kind of blood exists outside in the regular population, I'm going to say that this 0.00442 is equivalent to a fraction of 442 over 100,000. Now, how do I get that? I'm going to the end of the number and I'm going to see the last number, and it's in the 1, 2, 3, 4, 5th decimal place. So I'm going to have a 1 with 5 zeros on the bottom, right? Because this is the 10ths place, this is the 100th place, this is the thousands place, 10,000ths, 100,000ths. So I can do it that way, but I can also, so that it may be easier to count the decimal place. There's 5, put 5 zeros after a 1 on the bottom. So this is 442 out of 100,000. So that's not extremely likely. That's kind of rare, but it's not crazy rare. 1 out of a million would be very unlikely. So this is still kind of common. If I had 100,000 suspects, 442 of them could have supplied this blood. So I do want to, so we consider how that this might be used in a case of court.